Today we're going to look at properties of logarithms. Now that you've already worked with logarithms and switching back and forth between logarithmic and exponential form, we're going to now start learning some more techniques in order to work with logarithms. Because a logarithm is really an exponent turned inside out, or an inverse of an exponent, the properties of logarithms are all based on the rules of exponents that we did earlier first semester. The second thing to note, because you've not seen them and worked with them before, it does take a lot of practice to feel comfortable with logarithms. So I'm really hoping that you'll put in the time it takes to do that. And I find it helpful when I'm working with logarithms to keep reminding myself of which number is the base, which is the exponent, and which is the answer. In other words, in my head, I'm often flipping back and forth between exponential form and logarithmic form. And I find it helpful when I'm working with the rules. So the product rule. With exponents, the product rule tells us that when we multiply two powers that have the same base, we can add the exponents. Similarly, with logarithms, if we have log base b of m times n, we can split that multiplication into addition. And this goes back and forth, so we can also condense the addition into the multiplication. So looking at a couple of examples of doing this, if I have the natural log, or ln, of 7t, I can separate that multiplication of 7 times t into the natural log of 7 plus the natural log of t. Similarly, if I have log base 4 of 40, now there's lots of ways that I could split 40 up, but for instance, I could say that the log base 4 of 40 is equal to the log base 4 of 4 plus the log base 4 of 10. And if you recall from our introduction to logarithms, anytime I've got an equal base and argument there, that's the number 1. So this would be 1 plus log base 4 of 10. If you're curious about that 1, if you think about log base 4 of 4 and what that means as an exponent, that means that the base of 4 to what exponent gives me the answer 4. And so 4 to the power of 1 gives me 4, so I would replace that with a 1. Okay, so that's our power rule. And similarly, we have a quotient rule, and recall that when we've got exponents that have the same base and we're dividing them, we can simplify them by subtracting the exponents. And again, the same thing works in logarithms. When I'm dividing two logarithms, I could express that as a difference between the two logarithms. And again, it works both ways. If I have two logarithms that I'm subtracting that have the same base, I can combine them by division. So some examples of that, if I have the log of 19 over x, notice I didn't write a base with that log. When we don't write the base, we're assuming the base of 10, and that's actually called the common logarithm. So log base 10 of 19 over x, because those are dividing, I can turn that into subtraction. That gives me the log of 19 minus the log of x. And a second example of doing that would be the natural log of e cubed over 7 will be the natural log of e cubed minus the natural log of 7. We'll look further at how we can simplify this after the next rule. So the next rule is our power rule. And if you remember with exponents, when we did the exponent of an exponent, we could simplify that by multiplying the exponents. Here, when I have log base b of m to the power of p, I can pull that p out front and turn that into multiplication. So I've got p times log base b of m. So I'm going to do a few examples of that one so that you feel comfortable with it. So the natural log of x cubed is equal to 3 times the natural log of x. Speaking of natural logs, let's look at that last step, part of that last example from the previous slide. If I had ended up with a natural log of e cubed, well, that's 3 times the natural log of e. When we have the base and the argument of the logarithm being equal, this part is actually has a value of 1, so this gives us 3 times 1, which is 3. So that's neat to know that the natural log of e cubed is equal to 3. So that was our first example. Here's a little sort of second example looking back at that previous question. A third example would be the log base 5 of 7 to the power of 4 is equal to 4 times the log of base 5 of 7. Okay, so the exponent can just be pulled out front. So the natural log of the square root of x, it's important to think of that square root as what is the exponent. And if you recall, roots give us fractional exponents or rational exponents. So that's equal to the natural log of x to the power of 1/2. So now I've got the exponent of 1/2. I can pull it out front. So that gives me 1/2 the natural log of x. You do not need to write this middle step if you are comfortable with just doing the conversion. And the last example here, I've got the log base 10, so it's the common log of 4x to the power of 5 is equal to 5 times the log of 4x. So those are the three basic rules for logarithms. We're going to now practice using them, and we're going to start with expanding them. So we're going to start with a logarithmic expression and expand it using addition, subtraction, and so forth, using the rules that we've had done so far. Often we need to use more than one rule in each of these examples. So I've got log base a of s cubed times the square root of t. So again, we can express that root as an exponent. So that gives me the log base a of s cubed times t to the 1/2. So now I've got multiplication in here. I've got a product between s cubed and t to the power of 1/2. So I'm going to split those into addition. So that gives me the log base a of s cubed plus the log base a of t to the 1/2. And now I can use my product rule and, my quote power rule and take those exponents out front. So I've got 3 times log base a of s plus 1/2 log base a of t. And a second example, and feel free to press pause anytime here. Try it yourself on a piece of paper and see how far you're getting, and then press play again to check your answer. So here I've got log base 7 of the cubed root of x divided by 49 y to the power of 5. So I've got division here, and let's just remember that the cubed root of x is x to the power of 1/3, okay? So we're gonna, with that division, we can turn it into subtraction. So I've got log base 7 of x to the 1/3 minus log base 7 of 49 y to the power of 5. If you look at the second part here, I still have a product. I've got 49 times y to the power of 5, so I'm going to split that one up as well. So we've got log base 7 of x to the 1/3 minus log base 7 of 49 minus log base 7 of y to the power of 5. And I want you to ask yourself why I'm putting a subtraction there instead of addition. And be sure to ask in class if you haven't figured that one out. So now I can take all these exponents and pull them out front. So I've got, with the log base 7 of x to the 1/3, I've got the 1/3 out front log base 7 of x minus, now here I've got 7 and 49 is 7 squared. So that could be a 2 pulled out front, but log base 7 of 7 is equal to 1. So 2 times 1 gives us 2 minus 5 log base 7 of y. And then let's try condensing our logarithmic expressions. Okay, so we're starting here with a sum or difference of logarithms, and we're going to condense them and express them as a single expression. When you're condensing them, before you can use the product and quotient rule, you need to make sure that the coefficient of each of the logarithms is 1. And you'll notice that in example 3, how that's done, okay? And you'll see why that works. So let's take a look at our first example. I've got log base 4 of 2 plus log base 4 of 32. Well, because I'm adding, I can turn that into multiplication. So that gives me log base 4 of 64. 4 to the power of 3 is equal to 64. Therefore, this is equal to 3. And that's a good case of where using the properties allows us to simplify that logarithmic expression because its value is 3. Another example is log, and I'm just using the common log here. So if log of 4x minus 3 minus the log of x. So I'm subtracting, so I'm going to turn that into a division expression. So that gives me the log of 4x minus 3 all over x. And I'll just put brackets around it so it's clear that the logarithm is of the whole expression. If this simplified, this expression here, I would simplify it. And example 3 now, I've got 2 ln of x plus ln of x plus 1. Because I'm adding, I can multiply, but here's an example of where, because I have that coefficient of 2 showing, I want to make sure that that's a 1 first. So I'm going to bring that 2 and do the opposite of the power rule and express that as the exponent on x. So this gives me the natural log of x squared plus ln of x plus 1. Now I can do my multiplication. So I have the natural log of x squared times x plus 1. And I'll just put a second set of brackets around there to be sure that the natural log encases all of those. So again, remember that it's going to take a fair bit of practice to become comfortable with manipulating your logarithms using these properties.